Section 2 of Chapter 5 deals with exponential functions. As you can see from section 2.3, 5.1, we're looking at inverses of each other. Actually, I'll let you all catch up here. So I'm just already, I'm sorry. As you can see, actually, we've been doing this all along the semester. Those are inverses. Those are inverses. Those are inverses. So we've been dealing with inverse functions all along. Just that weren't really called those. Now, because we have to get into logarithms, what we're going to do now are exponentials and logarithms are inverses. This is what chapter 5 is about. Exponential functions. We've used the term exponential or exponent a lot. For example, we did something like this. This is the exponent. But that's not what the exponential function means. Here, the x variable is the exponent. An exponential equation looks like this. Where a is greater than 0 and a cannot equal 1. A has a name. It's called the base. So this is an exponential function base a of x. That's the official name of it. Now, the reason we don't have a, the base can't be negative, is because think of what happens. If a was -2 to the power x, what would happen when x changes from 1 to 2 to 3 to 4? Right. So exactly, it will alternate between positive and negative. Positive, it's called oscillating. So we'd have, well, no, let's use positives only. I'm not going to do negatives just yet. So when x is 1, we have -2. When x is 2, we have +4. When x is 3, we have -8. When x is 4, we have +16. The answer will fluctuate, positive and negative, positive and negative. Whenever the x is fraction or negative, it changes the whole thing. That's the reason a has to be positive. And it can't be negative. If it was 1, what would happen? If our base was 1, what would happen? It always stay 1. It's a pretty boring graph. It's a horizontal line. So I said a can't be 1. So let's look what happens here. It didn't say anything about the x. So let's say the base is 2 to the power x. Let's fill in those blanks and let's graph it. So when x is -3, what happens to that equation? Is what? Think of our rules of exponents. If you have a negative exponent, drop the negative and change the location. So it becomes positive 1/8. If we have x is -2, that's 1/2 squared, which is 1/4. 2 to the power -1 is 1/2, which is 1/2. What's 2 to the 0 power? No. 1. Anything to the 0 power is 1. When x is 1, we get 2. When x is 2, we get 4. When x is 3, we get 8. So the domain of exponential function is all real numbers from -infinity to +infinity. But the range has to be greater than 0. It can never equal 0. So anything in the negative realm, it's very small. Anything after 0 is getting larger and larger and larger. So that's an exponential function. That's what it looks like. Remember, a has to be positive, and it can't equal to 1. So if it's greater than 1, it looks like this. What happens if it's between 0 and 1? If a is between 0 and 1, meaning it's what? If it's between 0 and 1, what's the shape of it? What is the form of it? It's what? Oh, no, the number. If it's between 0 and 1, it's a fraction. So let's say that a is 1/2. Let's plot some points here. This is 1/2 to the power x. So what is 1/2 to the power -3? A negative exponent, if it's a fraction inside there, it flips it. So I drop the negative and I flip what's inside there. So now I have 2 to the power 3, which is 8. So I have 1/2 to the power -2. That negative sign flips the fraction, change it to a positive. So we have 2 squared, which is 4. 1/2 to the power -1. Flip that, so it just becomes 2 to the first, which is just 2. 1/2 to the power 0 is just 1. 1/2 to the power 1 is 1/2. 1/2 to the power 2 is 1/2 squared, which is 1/4. 1/2 to the power 3 is 1/2 cubed, which is 1/8. So what happens if it's a fraction? Again, when x is 0, it still crosses at 1, but it's a decreasing function. So if a is bigger than 1, if a is between 0 and 1, that's what the graphs look like. We just did examples 1 and 2. This is 2 to the power x. This was 1/2 to the power x. We can do transformations also. We can do transformations also. Look at example 3. Graph each of the following. Before doing so, describe how each graph can be obtained from the graph f of x equals x 2 to the power x. So A, 2x minus 2, B, 2x minus 4, 5 minus 0.5x. So let's look at A. What's this graph going to look like? Remember, think back of chapter 2 when we did transformations. Is it a horizontal? Is it a vertical? Is it a compression? Is it an expansion? Since we have, before we do anything with the function, we change x. So that makes it a what? What kind of shift? Horizontal. So it shifts to the right 2 spaces. So this is my original. It crosses at 1. It just shifts over 2 spaces to the right. The whole graph does. So it crosses at 1 there, but now I shift it over. What does B look like? It's a vertical shift because this is outside the function. Which direction does it go? Up or down? Down 4 spaces. 1, 2, 3, 4. So there's my new x-axis. Remember, it used to cross at 1, but now I shift down 1, 2, 3, 4. It intercept is there. All I did, take the entire graph, shift it down four spaces. Five minus 0.5x. Here's the exponential. What do we know about 0.5? It's a fraction. It's the same as 1/2. Remember, as long as this is between 0 and 1, it's a decreasing function. So the first thing we do is we look at 0.5x. That graph looks like this. It crosses at 1. What happened to it? Transformation-wise, what happens to it? Look at it. What's the next thing that happens? What does that negative do to it? Where? Is it inside or outside the function? Outside. So it affects the y values. It crosses at -1. This is 1. This is 2. Now, what happens to the entire function when I have a 5 in front of it? What does that 5 do? It's a vertical shift. Because it's outside the function, it's a vertical shift. It's the same if I put it back there. +5, but it could be in front too. So this graph, I shift everything up 5 spaces. So this horizontal line goes up 5 spaces. 1, 2, 3, 4, 5. The graph crosses 1 underneath it. So there's a graph. It's the same thing. Once you have the original graph, it's if it happens to the x value first, it's a horizontal shift in the opposite direction. If it happens outside the function, it's a vertical shift. If the coefficient of x changes sign, it's a vertical flip. Again, all this stuff is exactly the same thing we did in chapter 2. Now, applications. Example 4. Compound interest. We have 2 types of interest that whenever we borrow money, simple interest and compound interest. What's the difference? Okay, what's interest to begin with? Basically, it's a fee to borrow money. When you use a credit card, you're borrowing the bank's money. Well, you're actually borrowing your money, but the bank's fronting you up the money first. The interest rate to use that card is whatever your, how much? No, it now, see, this is upset, it's frustrating, is the government keeps on allowing banks to charge 15 to 27%. There's 27 cents out of every dollar goes to paying interest, which is criminal. Criminal, because the banks borrow money at 3% from the federal government, our taxpayer money. And yet they charge 27%, which is criminal. But these, well, we're getting robbed. Yeah, that's why I never ever use a bank. Use a credit union. Always use credit unions. Credit unions are smaller, local. They don't have to pay these huge vacation fees for the board of directors. Chase Manhattan, Visa, places like that. No, these huge banks, they have these board of directors, which are multi-billionaires already, or their family members or politicians, and they get paid huge salaries, 6 digits, to do nothing. And they have lavish vacations for annual retreats to see what the money is doing, and all they do is drink and have fun. It's criminal. It's criminal as all get out, and that's why I try to tell my students never ever use a bank, ever. Only use a credit union. When you become, if you become a teacher, teachers union. If you become, whatever. I mean, look at your neighborhood. There's usually a neighborhood credit union. It's lower interest rates on everything. It's better service because you don't have to pay all those exorbitant fees. But anyway, simple interest is just that. It's you borrow, P is the principal. That's the amount borrowed. Simple interest is you agree to a certain fee that you'll use that money for, or for however long, and then you pay that amount borrowed and that fee, and that's it. It's a one-time thing. Compound interest compounds it whatever the rate is at, whether it's daily, weekly, monthly, hourly, annually, quarterly. That's what N tells us. N tells us the number of times the principal is assessed. In other words, how many times the interest rate is applied to it. T is the time, usually in years. So if you take out a note, it's usually based on years. If you take it for 6 months, that's half a year. So it's 0.5. And so on and so forth. R is the rate, the interest rate. And N is, again, it's that amount you borrowed. And P out in front, that's the amount borrowed. So example 4. Yes. Usually your banks, if you have credit cards, they'll show you how much money interest you paid up until that marking period. And it's sad. I mean, your money just being going away to these people who don't deserve it. So it's just a pet peeve of mine. I can't stand banks. So in example 4, it says, suppose that you have $100,000 invested at 6.5% interest, compounded semi-annually. What does semi-annually mean? What's annually mean? Yearly. So semi-annually would be half a year, 6 months. Every 6 months. Yeah, so now instead of that 6.5% once through the year, it's actually a 13% interest rate for the year. It's a little bit higher actually because it gets jacked up once and then so this is not a good deal. And tell you, it's over 100,000. It adds up pretty damn quick. That's $6,500 interest every 6 months. And that's actually is pretty that's better than what we'd get. If we have $100,000, we'd pay it'd be monthly or annually. Or yeah, it's you have to read the paperwork before you sign anything. All right, so it says A, find a function for the amount of which the investment grows after T years. So A is A equals P, 1 plus R over N and T. So what is our P? What's our principal? The principal is the $100,000. That's how much we're going to invest. What's our rate? 6.5%. But you can't use percent, you have to use decimals. Percent means over 100. So 6.5 divided by 100, which means you move it over to the left. 0.065. N is semi-annually, so that happens twice a year. So our equation would look like this. Whatever T we have it for. And then the next one says find T at 0, 4, 8, and 10 years. So all you would do is, actually really is, you'd find this value in here and just raise it to either 0. The first one at T equals 0, the annuity, A is called the annuity. That's the amount that you owe. Or in this case, since it's an investment, it's the amount of interest that you get paid. So the annuity, when T equals 0, is simply 100,000. Because no matter what this is, 2 times 0 is 0. Anything to the 0 is 0. Anything to 0 is 1. So it's 100,000. Now, when T equals 4, that's when it gets complicated. You would change this to 4. So that's the only thing you change is here. And you type in your calculator. And then graph them. If we graphed this function, 1 plus 1 over n to the power n, as n goes to infinity, what would happen to our graph is we would taper off somewhere at 2.718. 2.71828. We call that number E, the exponential constant. It's used a lot in biology and the physical sciences because that's what we look at things when they grow exponentially. We're looking at that number. That's what we're saying here is for example, the COVID spread that we had, it grew in this realm. Eventually, it reached a plateau because everybody got sick. It couldn't grow any further, and eventually it'll go back down. So, in other words, whenever you see the letter E, it's a constant, like pi. So, like example 5, find each of the value to four decimal places. E to the 3. In other words, all you do there is take a calculator, punch the button, and you'll get it. Actually, you have these things here. I'll let you. This is what your calculator says. The rounding rule. What is the rounding rule? This one said the instruction says round to the 4th decimal place. Okay, so let's say we had a number 3.21728.159. Okay, if I said rounded to the 3rd decimal place, the 5th, and the 2nd. So what you do, go to the next number after the place limit. So if I said the 3rd decimal place, go to the 4th decimal place. If that number is between 0 and 4, drop it. And every number after it. So the number here would be 3217 because the 4th digit's a 2, so we just drop everything. If it's between 5 and 9, then add 1 to the place digit. Okay, the second one. We went the second, so we go to the 3rd. It's between 5 and 9. So we add 1 to the 2nd place digit. The 5th one, 1, 2, 3, 4, 5, go to the 6th. It's between 0 and 4, so just leave it alone. And graphing is the same thing. If we had this, it's the same, basically it's the same graph as that. If and if we had that, remember what the negative does? It makes it into a fraction. So then this one would look like this. So you treat it the same way we normally do. It's just it's a constant. And if you look at your calculator, you'll have e to the power x button, and you'll also have an ln button, as well as a log button. This is what we'll cover next. Didn't get as far as I wanted to, but oh well. All right, so go enjoy the sunshine while it lasts because it's supposed to rain this evening. Yes.
Well, on chapter four on the homework, it came out that the last two questions asked about critical values or like the critical, like.
Where the values are zero.
Oh, okay, I was like.
Because remember, we're looking for where it's above or below the x-axis, so the critical values are the x-intercepts.
Okay.
Those are the ones we're looking at specifically.
I was like.
Thought I explained that. I probably didn't. Oh, well. Yes, have a best day. Morning. We'll try to get some progress here. Yeah, unfortunately, this, I don't know where the time is, well, I know where the time is gone, but for this class, we'll finish these two today. Well, and these are all long, so I may push those off to the last of the course and worry about these and this, because these are the more important ones than these. We had a long time no see. Have you been okay?
I was on the Zoom last.
Yeah, yes, I saw you. I saw you. I heard you. We all heard you going. So yeah, we're making some pretty good progress. Is that unfortunately a lot of these are longish type sections. So, but we still have this week, next week, and the week after. I mean, we have plenty of time. So we'll try to finish this today. That one, so that's this week. Next week we'll do down to there, and then the week after we'll finish all that. So we have plenty of time. I was just trying to finish the semester early so you guys have a week to catch up your stuff. Even though in calculus, we really don't deal much with polar coordinates in calculus 1 and calculus 2. Laws of sines, yes. Parabolas, eclipse, hyperboloids, yes. And partial fractions, definitely. So out of the importance of this thing, this is the least important. Oh well, we'll see what we get. Let's see what we're going to do today.
Is a pencil?
How about a pen? Are you want a pencil or a pen? I don't have any pencils. I don't want to hurt you.
I can't touch.
All right, let's go ahead and get started. Enough people are here to get started. One person's all I need. Actually, my Cal 2 class, the students, they started more and more students want to sit down and watch it online so they can go to work. And so I'm just literally sometimes here by myself lecturing, and people are, and somebody walks in and says, "Who are you talking to?" All of a sudden, a voice comes in from above. All right, so let's get started. Laws of sine and cosine.